Hey, it's Mr. Allred, and we just talked about functions. We looked at them as graphs, and we wrote a couple, even though we may not have really understood how to write them at the time or what we were doing. But that's where we want to jump in now and actually see how we can write some of these functions, and more specifically, linear functions. So, as the name implies, linear functions, if we think about them graphically, will make a straight line. The notation for these you may be familiar with when we write the equation of a line y equals mx plus b, where the x and the y are points on a graph. So you can think about that relationship graphically. Or, as we want to talk about in function notation, f of x equals mx plus b. And in that case, you get the idea of the input-output calculation that the function would have. So this also implies that there's a domain that goes along with that. So in this case, the two things we haven't talked about here are m, which is a rate of change, and some people may have that in their head as a slope. But the rate of change is basically a change in y, or a change in the output, which we will call the rise, over change in the input, which will be the run. So this is basically a change in x over a change in y, or output over input. And that's what allows this to be a straight line, because that m will be a number. So it will always go up and over the same amount. Okay, so it will constantly be moving at a specific rate so that the line stays straight. And if m is positive, we'll say that that's a growing or increasing function. And if m is negative, we could say that is decreasing. Right? On top of that, the variable b there, well, it's not a variable, it's a constant. It represents the starting amount. Okay, so with some of our functions, we'll talk about where they start, or the initial value. Sometimes graphically, you may have this connected to a y-intercept in your algebra brain. Okay? So let's see here. Let's kind of go through an example here of a function and talk about everything that's happening. Timmy's class goes to the library every week and is allowed to check out 2 books at a time. Timmy's school year is 36 weeks long. Based on this, the function, let's write it down while we're here, b of w equals 2w. Now I chose to call it b for books and w for weeks. It can be used to determine how many books Timmy has checked out through a given week for weeks between 0 and 36. So his school week is only 36, his school year is only 36 weeks long. So it doesn't make sense to put in 40 because he is already out of school after 40 weeks. Okay? So we can see how that domain limitation between 0 and 36 makes sense. But what I want to do here is just kind of do some calculations. So let's do a few things here. Let's make a little table. Sorry, my line's not straight. But into it we'll put W, and we will put out the number of books, or BW. Now, I'm going to use even numbers just because of the way I had to graph this thing. The grapher I was using worked alright, but I couldn't zoom in too far or I lost a lot of things. So I'm going to plug in numbers for the weeks and calculate the books, and then we're going to relate that over to the graph. So 2 times W is the calculation. So when W is 0, before he ever starts checking out books, he has 0 books. At 2 weeks, 2 times 2 is 4. Okay. At 4 weeks, 2 times 4 is 8. 6 weeks, 6 times 2 is 12 weeks, sorry. And 8 times 2 is 16. So I can plot these points over here just to kind of show you how everything relates to the graph. So 0, 0, and notice my scales here. The bottom is going to be weeks, and the side is going to be books. Okay. And also notice that if you go from 0 to 10, it looks like we're counting by 2, and that's why I did my table by 2, just so it would line up with the graph. So here is 2 for weeks, and here is 4 for books. So make sure you see that. And then 4 for weeks will be 8 for books. 6 for weeks will be 12 for books to kind of emphasize. And then 8 and 16. So what you see is all these points make a straight line. Now, I did kind of skip some points here, the 1, 3, 5, 7. And that was because if you look at this thing in the perspective here, let me just change that. In the perspective of y equals mx plus b, the m is 2, which can be 2 over 1, which means it's increasing at a rate of 2 books per week. So as long as it's consistent, that means it's going to go up and over, up 2 for books and over 1 for weeks. So it's going to do that consistently, and it's going to have a nice straight shape to it. Now the b here we don't see in the original 2w, but that must mean we're adding 0. So the b equals 0 means he starts, let's clean that up. With 0 books. So just making sure we see those two things. Okay, and that's where we have, and if you're familiar with the y-intercept, you see it on the y-axis there. Okay, so let's go through another example, maybe a little bit better, so we don't have to do all the graph, but we can write the equation. Let's see here. April is running a marathon to raise money. She receives $300 in donations and pledges that commit to $10 for every mile she walks. Okay, so it says write a function to determine the amount of money she raises based on the number of miles she walks. So let's see if we can do this. So she's going to raise money, so that's what we're trying to calculate. So let's make our function name m for whatever reason. Big old M. And she's making money based off of how many miles she walks. Ugh. So there's a little m. Let's just call it a W for walks. Okay. Now, if we try and relate this to a y equals mx plus b, we're trying to think about what's happening here. There's a starting amount that she has before she ever starts walking. Okay. And in this case, that's 300 for the starting amount. Okay. And then the rate is for every mile she walks, she's going to get $10. Okay. So let's see. That function would look like 10W, since I'm calling it walk, plus 300. So she gets $300 up front from the way this is written if she doesn't walk at all. And then she gets $10 for every mile she walks. And when we asked how much money will she raise, we just kind of named our function accordingly. So in this case, 10 is the rate, and that means it will grow 10 for every mile she commits to. But it'll also have that extra 300 on it. So on a graph, it would start up at 300, and then it would go up 10 over 1. And then when we try and do the second part, what if she walks 20 miles? We'll plug that in. 10 times 20 plus 300. So that will be 200 plus 300 will equal $500. And that's how much money she would raise in total. Okay. So it was $10 per mile. So what that means is it's increasing by $10 every time she walks an additional mile. Okay, so we have a starting amount of 300, and we have a rate of 10. So look for those two things. All right, let's do this example. Terry has 48 cars on his lot. He sells an average of 3 cars a day. Write a function showing the number of cars he has left after so many days. So we're assuming he's not getting any more in. So let's see here. What can we do here? Well, we're trying to calculate the number of cars he has, so we'll call our function C. And the thing that's changing here is the number of days. So we'll call it C of D. Now in this case, when we look at things, he has 48 cars to start with, so that's a starting amount or an initial value. Okay, and he also is selling 3 cars a day. So that is the rate of change. But let's kind of keep in mind here, he is losing 3 cars per day. So what does that mean? It's negative 3D for days plus the 48 that he started with. So he had 48 to start with, and he's losing 3 every day. Sometimes that might look better if you said I start with 48 and I'm going to subtract 3 every day. So at 0 days he still has 48, that's when he started. At 1 day he's going to subtract 3, so he'll be down to 45. After 2 days he's going to subtract another 3, so he'll be down to 42, and so on. Okay, and it says, is there a domain restriction on this function? Okay, so let's see. He cannot sell more cars than he has. So if we're going to talk about this as a domain, the least amount of days this function would work for would be 0. Would be when he first starts off and still has all his cars. But we can't put in 1,000 days without him getting some more cars in, because then he would sell more cars than he ever had. So let's just kind of see. This 48 minus 3D. He can't have less than 0 cars left. So we'll just kind of set that equal to 0 and solve it, and I believe this gives us 16. So the domain of this thing is D would have to be greater than 0, but less than or equal to 16. So this function could only work for the first 16 days. After that, he either has no cars, or he has to find some way to rewrite the formula and get more cars. Okay. So we're going to stop there. We're going to stop there, and we're going to pick up with some more examples on the next. But just kind of keep in mind. Just kind of keep in mind. Sorry, wasn't expecting that to happen. Just kind of keep in mind that we're writing the function, and we have the M for the rate here, and the B we're writing is the starting amount. Okay, just kind of keep the meaning of those two things in there when you see them.